Okay, well, I'll do that. Oh, minimize that. Okay, here we go. So hopefully we'll be able to slideshow. Like I said, for those 3 people that are not in the wood class, the first few slides are going to be very repetitive for a lot of the people. So I left the captions on, the subtitles. So if you want, I can turn them off if you find that they're distracting, but it's up to you. Anyway, so like I said, this is from wood. This is somewhat of a repeat. Like as I said before, limit states design is the design method that is recognized by the National Building Code. Prior to I think prior to 2000, there was 2 design methods. The other one became obsolete. And now limit state design is the only design method that the National Building Code recognizes. Okay, so so of course, a design approach to provide adequate resistance for strength and serviceability. And like I said, we will, and both in the steel and the wood, we will be, doing both, doing the strength, checking the serviceability, and making sure that the member can perform adequately under both conditions. Now, of course, the strength is the resistance, and they call it ULS, ultimate limit states. And of course, this is where you design for, strength capacity, overturning, sliding, and fracture of a structure. And then serviceability limit states is to make sure you don't have excessive deflection so that any materials that are supported by your structure will not experience cracking, vibrations, permanent deformation, and local structural cracks. And like I said, I will not do anything on vibrations. Vibrations become an issue when you start getting into some very long spans. What I mean by long spans is if you're talking about 10, 12, 13 meter spans, and you're using very, very light members. Like for example, if you're using open web steel joists, and those of you that don't know what open web steel joists are, you will definitely know what they are by the end of this morning. And especially if you have long spans and you have very light members, you can get into a vibration problem. And of course, they're more of a nuisance than anything else. You can have it will be adequately safe to carry the people that are sitting on the floor, but then the people are going to be complaining because as you're sitting down, the guy that walks next to them, they can feel the vibration in their chairs, and that becomes a little annoying. So like it's more of an annoyance, okay? And of course, the excessive deflections, the materials that are going to be supported by the members. If the deflection is too excessive, certain materials are very, very brittle. For example, if you have masonry walls, that's a very brittle material. If you have ceramics, if you have glass and so on, these are all very brittle materials that can take very little displacement, and therefore if the material is being supported by something that has excessive deflection, it's going to crack. And that people don't like to see cracks when they buy their homes or they buy their buildings, and therefore that becomes another issue. So now loads, of course, we will categorize loads into, a load is of course the imposed forces and pressures applied to a building structure. And of course, the 3 categories of loads are going to be what we call the permanent load, and people call this also the dead load. I like the word, like in French, when we say dead loads, it's not une charge morte. In French, when we say dead loads, it's une charge permanente. So I like the fact that in French, you actually use a permanent load as opposed to dead load, but all the textbooks talk about dead load. And variable loads, of course, are the ones that change in magnitude, direction, and location, and that would be your live load, your snow load, your wind loads. Those all can change in direction and locations and so on. And of course, the last one is the rare loads, which is earthquake loads. And these only occur very infrequently for a short period of time. And this is the earthquake load. Now, as far as the loads that you have to consider in the structure, the National Building Code, these are what they want you to consider if they are present at the time, or they will be, during the life of the structure, if they're going to be there. Otherwise, for example, dead loads for sure are always going to be there. So the weight of the member itself, is a dead load. Anything that's permanently attached to that thing is a dead load. And then, so, and the earthquake loads, like I said, beyond the scope of this work, of this program. But if you have a light structure, very good chance when you have a light structure made out of wood or steel, in many cases, the wind load will govern over the earthquake load. So you have to do both calculations, but if you design it for wind adequately, it has a good chance that it's already meeting the earthquake resistance, and especially wood structures and so on. So now, then of course, a permanent load due to lateral earth pressure, including groundwater. So, I mean, you know that this is only going to be for walls and stuff, basement walls and retaining walls and so on, swimming pools. If you ever design a swimming pool, you'll have to take this into consideration. And the live load is a variable load due to the intended use and occupancy. And of course, this is like listed on the National Building Code, the minimum live load that a floor has to have. And I stress the word minimum, okay? That doesn't mean that if you use what the code tells you to use as a minimum and something goes wrong, you'll be exonerated. At least you'll be exonerated up to a certain point. But then after that, it was up to you to judge whether that minimum live load was sufficient, and you had to judge whether or not you wanted to use a higher load. So keep that in mind. And permanent effects caused by pre-stressing. Of course, this is people that get into pre-stressed concrete or whatever. Okay, there is an effect caused by that, and that you have to take into account. And the reason why they divided these, because all of these have different load factors. That's why they break them down into this. And a variable load due to snow, including ice and associated rain. Of course, up here in Canada, up in Canada, we happen to, live with snow load. Now in Quebec, I don't necessarily worry about rain load in Quebec, because I find that snow load tends to be the one that governs the design. But there's certain provinces, guys, you'd have to check both the snow load and the rain load and see which is the one of the two that you have to design for. So there's it's not this associated rain with the snow that you kind of add to the snow load. It's a complete rain load that you have to calculate that your roof can be subjected to. And that's another thing you might have to consider. Now, effects due to contraction, expansion, deflection caused by temperature changes, shrinkage, moisture changes, creep, ground settlement. Okay. So these are, of course, things that wood is a material that is not a natural material. It does get affected by moisture, and therefore if you're going to be in a place where you're going to be changing the moisture content of the wood, make sure that you leave room for it to expand, to take account for the moisture changes and so on. If you're going to be designing something outside, remember, here in Quebec and anywhere else in Canada, you can go from -40 in the wintertime to +40 in the summertime. So your delta T, your changes can be quite sufficient. So you either have to design for those temperature changes, or you accommodate them and you make sure you put in some, expansion joints. That's, so you either design for it, make sure this member is strong enough to resist it if you can't allow it to contract or expand because of an expansion joint, and so on. Okay. And then after that, of course, the wind load is also a variable load. And the nice thing about it is that the National Building Code still takes this very dynamic load and has a nice way of making it to a static load. So therefore, it's easy to quantify and to do the analysis with. In the past, just to give you some history, in the past, the National Building Code also had a static way of doing earthquake loads, but that's been abolished. And now everything has to be done by dynamic analysis. There is very, very specific buildings. You can still do it with a static analysis, but it's very, very limited. So that's why I don't even want to get into earthquakes, because you guys, dynamic analysis in itself is a course in itself, okay? Now, of course, the other thing that the National Building Code does is that it has importance factors for the snow, the wind, and the earthquakes. And of course, okay, now what like I said last time, and I want to stress it here, okay, is what I want you to note in the importance factors, okay, is the fact that, okay, so these are the load factors. In other words, if it's a school, you increase it by 15%. If it's a post-disaster building, such as, fire station, police stations, radio stations, you increase those by 25%, okay? And then, of course, what you have to keep in mind is that this is for strength. This is you, okay? And then look, for serviceability, you actually will reduce, okay, your design load for serviceability when it comes to snow, okay? And wind is the same thing. In other words, you increase for the design of strength. And look, as a matter of fact, you reduce the wind load by almost you actually reduce it by 3/4 when you want to design for serviceability, okay? And we will be doing this in the wood class for the exterior walls, and I'll show you how to apply that. And of course, we're not going to talk about this at all, okay? Okay, so post-disastrous buildings, okay? So like I said, these are fire stations, hospitals, anything that has to stay up after a natural disaster. And, and of course, high buildings are like schools, clinics, whatever. I think clinics probably fall under post-disaster. Normal is everything else, all buildings except those, I like the way they say this, but the normal buildings, of course, are residential, office buildings, and so on. And this here, I would totally disregard, okay? Low, don't even bother. Because if something happens, even if you say, well, the code allowed me to design this little building, you'll have to answer to that, okay? So I never even bothered with this, because like this, when you're designing a barn, you're allowed reducing your load because it's only animals. I've seen barn collapses, guys. I've investigated them, and it's sad to see a couple of cows that died under the collapse of the building. So, not that I'm an animal lover, but I believe that if we can save anything, we should. Fair enough. Okay, so now. Okay, of course, the load combinations, we talked about this, and this is, okay, and like I said, here, okay, this is for overturning sliding, okay, so don't worry about this. Like this, you only worry about this when you're overturning or sliding, right? And the thing is that, when you have a principal load and you have a companion load, in other words, if you have both a live load and a snow load, a live load and a wind load, and so on, this is how you combine the two, okay? And of course, we won't even talk about the earthquake load. So I find it, because when they do like this, it's very confusing. And what here, just to give you a quick overview, what they mean by this is that when I have a structure here like this, okay, and if I have a lateral load by wind or earthquake, whatever, okay, you can appreciate that the gravity load of the building helps to resist the overturning moment caused by the lateral load. So therefore, they want you to reduce that resistance of that force, and that's why they want you to reduce the dead loads by by 10%, so that you can assure yourself that this overturning resistance that you're basing yourself on is a little bit safer. That's why they have this lower. And the same thing for sliding, because when you have sliding, your gravity load is what causes the friction, okay, and therefore you want to make sure that that frictional force is capable of resisting your lateral force. Okay, now, okay, and then of course for serviceability, what I want you to realize is that you always use the specified load, okay? So in other words, you don't factor the loads like you do for strength. You always use the specified load. That's why all these factors are 1. And of course, where does it change? Well, when you have the wind, remember the importance factor here is 0.9, and therefore the snow load changes because of the importance factor, but the load factor stays the same, and the same thing for wind. And this becomes 0.75, but this stays the same, and that's where these change. And also you should note that where you have your, for example, when it's the wind, you're combining it with either your live load, okay, you reduce that by 40%, and then when it's the snow, you reduce your live load by 50%, okay, and so on. So if ever you have this situation, that's where these, that's how you combine these load combinations. Like I said, they should call this not load cases, they should call this load combinations, because because there really are different load combinations, not really different load cases. I find that's a little misleading. So, okay, now I think that was pretty much what we did in wood also. Oh yeah, adequate bending stiffness shall be provided so that the maximum deflection of a member does not exceed the values in the following table. Now, there's a table for wood, and then there's also a table in the steel handbook, okay? Deflection criteria. So this is what you see in a steel handbook. Okay, so here is I'm trying to find, okay. So basically, for steel, you look at the type of building. If it's an industrial building, and as a matter of fact, that's going to be our project. We're going to be designing a small industrial building, okay? The vertical deflections, in other words, any deflections where you're going to be applying gravity loads, the vertical deflections, okay? They say the member supporting inelastic roof coverings, you can have a maximum of L over 240. So in other words, delta max is L, which is your span, over 240. So if ever you're designing a roof and you know you're not going to have anything attached to it that's going to be susceptible to cracking, you shouldn't go more than L over 240, okay? And if all of a sudden you have a roof here, even if it's an industrial building, you have a roof here, and then if the architect wants to put some drywall attached to the underside of your structure, then you shouldn't use L over 260, you should be using L over 360. And that's what you should limit your deflection to, because the drywall is susceptible to cracking, okay? And then of course, members supporting inelastic, these are very, very, snow load for floors, okay? Now this is where, you can see how severe it is when it comes to cranes. The cranes are very, very severe, L over 800. In other words, you got to make sure that when you're designing your crane beams or the rails, that you have to calculate where the crane is going to cause the biggest moment, and you have to make sure that that deflection does not exceed L over 800. So see how severe it is for a crane. Now, maximum wheel loads, 600, okay? Now, it's unfortunate here because they don't say this, but I'm telling you, like, if ever you have a steel, for example, sometimes you might have to have a masonry partition sitting on your steel structure, okay? And I think some people say L over 600. I always design that for L over 720. I make them very stiff, so I don't have any cracks in my masonry. They don't even talk about it here, which is somewhat misleading, okay? And of course, for all the other ones, it becomes a little bit more severe. So you can see for like the L over 360 as opposed to L over 300, okay? So I do recommend that, stick to L over 360 as a minimum when you're designing your live loads. Don't even go to 300. And after that, depending on how sensitive your material is, go to L over 480, go to L over 600, go to L over 720, and so on and so on, okay? So this should be like almost the maximum or the minimum that your stiffness should be, okay? And then of course there's also loads for lateral drift. In other words, that's what these are, okay? So L would be the height of your building. Or in other words, so therefore this is for lateral displacements and so on, okay? And the same thing here. So that's it. And like I said, they're pretty repetitive. And here, sometimes they say that these are suggested values. They're not required by the standard. Yes, that's true. They're not required by the standard, but they are, like the L over 360 is required by the National Building Code when you have materials susceptible to cracking. So even though it's not required in the standard, it becomes required in the National Building Code, and therefore you might as well conform to it. And that's why sometimes I find these things are misleading, because you follow this, it tells you to do one thing, you forget what the National Building Code tells you to do, and something goes wrong, and then all of a sudden you're going to get blamed for it. Okay, so any questions on deflections? Like I said, we're going to be applying deflections throughout all our beam designs and so on. So we'll be applying these to our design, and I hope it's now. Oh, sorry. I made a mistake. Hold on. Last viewed. Okay, now, structural steel shapes. Okay, so guys, this is something I want you guys to really start getting familiar with. Okay, and And here we go. Okay. Now, in structural steel, okay, we have designations. For example, we have WWFs. Okay. So if I look at a drawing and I see a designation WWF, it's not the World Wrestling Federation. That's not what it is. It's this here. Okay. So when I see this on a drawing, in my mind, I already see the cross section of the shape, okay, of the profile. And a WWF is basically made from plates that are cut at a certain size, okay, and that's why they call it welded wide flange, because the flanges, and of course we know that this is a flange, this is a flange, and this is a web. Okay, so those are that's how you refer to the different parts of a shape. So this is flange, flange, and web. Okay, and if you see here, the web plate is welded on both sides to the top and bottom flange. Okay, so the first letters gives you an idea of what the cross section of the shape looks like. The second number tells you what the nominal depth is. In this case, for the white flanges, it's the actual depth, but this is what they call D. In other words, in this case here, this D is 2 meters high. I don't know if you can appreciate this, but that's one hell of a beam, okay? So a 2-meter beam. So that's what this is. So in other words, this one would be about 2,000. Well, this one in the white flanges are exactly that, but in the other ones, they're called nominal depths. And this is what this thing would probably ends up weighing per, understand? In other words, this is the biggest section that they have, and it weighs 732 kilograms per meter. So therefore, if you, for example, if I see a WWF 2000 by 732, that means it's a welded white flange section. It has a depth of 2 meters and it weighs 732 kilograms per meter. And I don't know if
Sir,
yes.
what would a beam of this magnitude be used for commonly?
This is like when you get into designing pulp and paper plants where you have a heavy machinery sitting on the floor. You understand? Like this is like very, very heavy industry. Understand? Like in other words, where you have your loads are going to be excessively high, your spans are going to be excessively long. Understand? That's where you would consider using welded white flange shapes.
All
Okay,
right, thank you.
so
Because I
so
was
no,
really taken aback, but this beam is wider than I'm tall.
yeah, exactly. Like you'd be standing next to it, and I too would not be able to see over the beam. Understand? And I'm glad you appreciate that. This is I used to call it BFBs, you understand? And I won't say what the F stands for, big blank beams, you understand? And these are big. And like I said, this is mostly like in heavy industrial buildings where, like you need to have this type of capacity. That's where these things would be used, okay? Now, you also have what we call welded reduced flange shapes, okay? They're very similar to here, but the top, sorry,
I have a question.
go ahead.
Why would like say the difference between like W shapes and welded wide flange?
Yeah.
Why would you use the welded one instead of?
No, we wouldn't use the welded one. You understand? That's like a very, very specific. That would be for a very, very like these are for like very, very heavy industry buildings. You understand? The difference between if you're asking me when would you like most of the time you would use this one here. Okay.
Yeah,
Okay, most of the time you use this one. And now, do you know the difference between what's the significant difference between this one and this one? Is
one
that
is welded, one is not.
well, yeah, but these things, believe it or not, they start off like this, okay? They start off like that, and then they go through a series of rollers and they end up looking like this. Isn't that
Okay.
amazing? So that's why they call it, you understand? These are all rolled sections. In other words, in the mills, the steel sends it down. They have a series of rollers, of course, like the first roller will probably just make a small dent like that, you understand? And then the second roller makes, and these things get rolled, you understand? So these are rolled shapes, whereas these are the plates, like they have big plates and they're cut and then they're welded at the top and the bottom, okay? Now this one here, okay, you use a reduced weld flange when you know that you are going to be pouring a concrete deck. Let me just, hold on a second. Like when you're going to be pouring a concrete deck over your beam, and then you want to have shear connectors here, and we'll see, you'll see what shear connectors are, and then you want to have the concrete slab being composite with your steel beam. So what's going to happen is that since this concrete is going to be replacing some of this bottom flange, you don't have to waste that steel up there. Okay, so that's why we have welded reduced flanges. And especially when you have composite sections, it becomes a little bit more economical to order these. So this is used for when you want to have your concrete deck compositely connected to your steel frame, and they work together as a composite material. And this in itself, it's not very hard to design, but like there's a few things that you take into consideration, the creeping of the concrete and so on, and everything else. But it is like, if ever you guys happen to be driving by a highway and you see those steel girders that are going to be supporting the overpass, and if you ever look on top, you always see that there's always shear connectors on top of those girders, and that the deck of the overpass always is designed as a composite section with those girders, so that they're working together. So that's something that if ever. Now, this here, of course, the W shapes, okay, see, you can appreciate, look, the biggest W shape you can get is 1.1 meters, which is still significant, okay? And then I think it can go all the way down to 100. So it starts at 100 and it goes up to 1,100, okay? As a matter of fact, if you guys ever, if you, like all the different shapes that are available, those are like, if ever you go to ADA and when you pick a shape, all the W shapes, they're all in that database of that program, okay? And that's, so now here the same thing, okay? So W means it's a wide flange shape, and these are rolled sections. And again, the first one means that now here the 2000, this would be exactly 2000. That if my memory serves, these represent exactly 2000 in depth. Whereas in the wide flange, okay, the 1100 is what we call a nominal depth. Okay, it can be slightly bigger, it can be slightly smaller. I mean, what I mean by bigger, it can be 1105, or it can be 1997. They are not, this is just a nominal depth. It's approximately that, and each shape will have there's tables where you can get the exact depth if you need to have it, but it varies, okay? So this is a nominal depth, and of course, again, this is the mass per unit length. So therefore, this is the biggest W shape you can have, and so on, okay? So these are the ones that you would use to make beams with in buildings, and these are the ones that are most commonly used, okay? Now, HP shapes, okay? You guys have heard about soldier piles? Who doesn't know what a soldier pile is?
I don't.
Okay, when you want to make a retaining wall, okay, you take these soldier piles and you drive them into the ground, you understand? And then you put wood lagging in between, and then you can start excavating the earth, and that acts as a retaining wall. You didn't cover like retaining walls in your construction 1, your construction 2 classes?
We did. Yeah, we covered shoring walls.
Okay, so in other words, the shoring walls, like the ones where you have a steel, call it a beam, a column, a shape, okay? And those get driven into the ground. And that's called a soldier pile, soldier pile shoring wall. Now, the HP, okay, like in this case, in the W's, like these flanges can be relatively narrow compared to these depths, okay? So in other words, when you're looking at a shape here, like this, Okay, sorry. Now, this dimension here is called dimension B, and this dimension here is called dimension D, the outside to outside dimension. So that's B and that's D. So if you want to know the width of the flange, you find that on the table, but that's always designated as B. If you want to know the depth in the table, they'll give you the exact depth of D. Now, so these can, like for example, this can be 156 millimeters, and this can be 200 or 309 millimeters sometimes. Okay. Now the HPs, the B and the D are approximately the same. So in other words, if I have a W360, okay, that means that this here measures 360, and most likely the width here of this flange measures 360. And the reason why that's the case is because when you want to put in the wood lagging to do your soldier piles walls, you need to have an area for the wood to bear against, and that's why they always use HP for soldier piles. Okay. Now M is the same thing as W shapes, very miscellaneous. In other words, it's I never use them, but these are like very close to W shapes, and it's miscellaneous steel. And then of course you have the super light beams. Okay, so in other words, these are very small. Like you see, it's 100. That's the biggest one you can find. 100, which is 4 inches by 5.4 kilograms. So if ever you get into like you want to make a series of joists that are spaced very close together, and you want to use super light beams, people tend to use channels in that case instead of beams. But so you have super light beams, so SLB, M, like they're available, but very rarely are they used. Most of the times people will use this because it's also a question of availability. Okay, these are probably not milled very often, and therefore you might have to wait until it gets done, and so on. So these are, like I said, and then there's, hold on, I think there's some more. Last viewed, okay. Yeah, I'd rather do this. Now, the other shapes that you have in structural steel, of course, are S shapes. What does this look like, guys? What letter does that look like?
I.
I. Okay. In the past, they used to be called I-beams. It makes sense, right? And then in the 70s, because the computers were using 1 and 0s as a binary numbers, and the I was being confused for a 1, they changed the name from I shapes to S shapes, standard shapes, okay? And now these are, they're relatively good beams. You see that the flanges are tapered. You see how the flanges are tapered here? These are used mostly for, when you have overhead cranes in buildings, that's where you use these for overhead crane rails in buildings, okay? Because the if I can draw it properly, but like the wheels of the wheels of the crane that roll back and forth, you understand? They roll very nicely on this flange, and that's where they're used. And then of course the crane is here like this, and there will be another one on the other side, hopefully. And that's where these are used mostly for, rails of overhead cranes in buildings. Okay, I've also used them, for example, in elevator shafts. I've used these myself. So like they are used, but the most predominant use of these things, like I said, are for the rails of overhead cranes in buildings. Now, channels. Okay, so a C, of course. Okay, it looks like a C. Okay. And again, this is the nominal depth and the weight. Now, the channels are the same thing, okay? In other words, this means that this is going to be, this one goes up to 310 millimeters, in other words, 12 inches. That's the maximum size channel you ever get. And the maximum weight that you'll ever have is 45 kilograms per meter. And then at the same way you have standard channels, you have some miscellaneous channels, which, sometimes can go up to 460, okay? And like I said, if you're going to start using the miscellaneous because it satisfies your design, you better make sure they're available. Okay. And in French, these are not called C. Okay. In French, these are called U. Okay. So if you're looking at the French, okay, and you want to refer to a channel, remember in French they use U, not C. Okay. That's what they use in French. They say the U and not the C. So that's how you say channels in French. And angles. Now, the angles, what I want you to realize is that angles can be unequal legs, like here, or you can have angles with equal legs. In other words, this dimension and that dimension are exactly the same. Okay, so you have two types of angles. You have ones that have unequal legs, and you have ones that have equal legs. Okay, and of course, the first letter designates D. The second letter designates D. And of course, if you have equal legs, this would be 203 by 203. And this here, the 13, represents the thickness of the legs. So this is called a leg. Okay. And this is T that only represents the thickness. So thicknesses go from like, I don't know where they are in well, 6.4 millimeters. It's a quarter of an inch, quarter of an inch, 5/16, 3/8. And, you know, like, these are all still being manufactured in the imperial sizes. That's why you see all these numbers being, you know, you don't see 200 by 150. They're still being milled in the imperial sizes, and therefore they're just being converted to the metric size here. So this would be 8 inches by 6 inches by a 1/2 inch thickness, you understand, which is 12.7. So that's what this is. So the real, okay. Now these are angles, and of course we'll be using these angles. We'll be designing connections with them. So we're going to be using some of these. Clear the drawings. And of course, structural T's, okay, WT. Now, all this is, in other words, if I take a 460, okay, if I take a 910, I simply have to just double this number, okay, 920, I should say, and double that number, and I cut them in half. So in other words, I take a W920 by whatever it is, 255 times 2. I can't. That's by 440. 450. Anyway, if I take that shape and I cut it right down the middle here, this becomes a WT and that becomes a WT. Okay. Now, where do we use WTs? Well, if ever you're doing a truss, if you want to fabricate a truss, WTs are very, very nice things to use as your top and bottom chord, because this is your flange of your truss, and then whatever web members you want to come, you can connect them very nicely to the side of the stem here. This is called the stem. Okay. And so these are very, very common, used for fabrication of trusses, T-sections, and so on. Okay. So those are WTs. They're just white flanges cut in half. That's all they are. Okay. And then the other shapes that are produced in the mills, of course, are HSSs. Now, HSS stands for hollow structural steel. Okay. It's not, it doesn't stand for hollow structural shapes or sections. And anyways, hollow structural steel. And of course, there are 3 types that are made. Okay, you have rectangular, you have square, and you have round. Okay, and the way that these things are designated, they don't show it here. It's unfortunate, but these things are designated. Like, for example, if you see 205, I think it's 205 by 205. I'm sorry, but like in imperial, okay, 152. This I know, 152 by 152 by 6.4. Well, that means that this dimension here, this dimension here is 152 millimeters. This dimension here is 152 millimeters, and the 6.4 is the thickness of the wall. Okay, and of course, you have round, you only see 152 by 6.4. That means it's a round shape, and the wall thickness here is 6.4. And we will be using these to design the columns in our buildings, and we'll also use them to design columns in our subject. So that's why we'll see these HSSs, and then I'll go into more detail of the different types of HSSs that are available from the mills in terms of the classes and so on. Anybody have any questions on this? Like I said, guys, this is something, if you guys are going to get into the, well, I know you're all going to get into the industry, and, you know, those of you that are planning to become project managers, like you're going to have to get to know all this glossary, understand? Because when you're going to be talking with the structural engineer at the end of the phone, the more you can be specific of what you want him to do or asking him, the more clearly you're going to be able to express yourself to them. So it's the more you learn about the glossary of any field in civil, understand, in the construction industry, the simpler you're going to be making your life, either when you want to discuss with somebody, or if you need to write up a memo, you'll be very specific and you'll be addressing it correctly, and so on and so on. So, I mean, yeah, it's easy for me. I've been around for 40 years. I've been seeing these things for a long time, so it's easy for me, but it will come. And the more you force yourself to remember this glossary, the easier it's going to be for you during your career. That's all I suggest. So people think, well, I'm not going to become an structural engineer, I'm not going to be interested. Yeah, but if you're talking at a meeting and you want to be specific on what you're saying to somebody that's sitting at the meeting, I mean, I've seen people give me a call and said, hey, your column is all screwed up, and he was referring to the beam in the ceiling. So I was picturing this vertical element in my mind, and he was pointing at a horizontal element up in the sky, just to show you how, how do you expect me to understand what he's asking me if he's talking about a beam when he refers to it as a column, So, okay, so let me clear this. Now, one last thing. Last view, okay. Now, this is something that I found. I had this in my steel book, and I figured, oh yeah. Now, here are, let me just move this over because it's in my way. Okay, here are the different types of steel that we use, in steel structures. Okay, and this is 7 types covered by the CSA G40.21. Of course, this is the CSA standard that will tell the mill how much carbon, how much iron, how much nickel, how much this, how much that, so that they can produce the right quality of steel. Even when they roll the section, it specifies what's the tolerance. In other words, if my flange is supposed to be 8.2 millimeters, it can't be less than 8 point whatever. It specifies the thicknesses of the walls of the HSSs. So all of that is specified in this standard, CSA G40.21. So if this is what you refer to on your drawings, all steel to be at a CSA G40.21, then the guy that's going to be ordering the steel has to assure himself it's being done from a Canadian mill. And I'll tell you that the American mills are not as good as the Canadian ones for certain shapes, and we'll talk about that during the course. Now, the most common one that we use, okay, for the W shapes is here, type W. So in other words, when you see, CS, like, and if you see a standard, like you see CSA, this is what you always put on a drawing. CSA, well, G, this is no longer done. I'll tell you why when we talk about beams, okay? Okay, 350, W, well, this stands for the yield strength is going to have 350 MPa, and this is the type of steel, weldable steel, okay? So the steel has to be weldable, because if you want to be able to connect it to something else, you have to be able to weld it. So that's weldable steel. And this here is the most common steel, okay? For buildings, compression members of bridges, and so on, okay? So this is the most common steel that we have, okay, that you find. Now, if temperature becomes a big factor, especially when you're designing bridges, temperature can become a big factor. You can have WT, tough notch steel, okay? So there's tests to see so in other words, it performs very well at very, very cold temperatures. So this is when you get into, okay, application includes primary tension members in bridges and similar elements. That's where you would be applying that one. Now, type R, okay, is just corrosive resistant steel. Now remember, the difference between R and A, well, this is corrosive resistant steel, but this one is weldable. So if you don't need to weld anything and you want to, this is the one you want to use, okay? And if you do want to weld a corrosive resistant, then it would be a type A, okay? So this is for, and I'm trying to remember. What's nice about this steel is that once it's in place and it starts to corrode, believe it or not, the surface corrodes, it looks like a darkish brown, And that surface corrosion actually protects the rest of the steel from corroding anymore. It's amazing. It's pretty nice. I'm trying to remember where in Montreal, if you guys ever happen to be, I think I'm trying to remember they used this in 1967 when they did the bridge going from Ile Notre Dame to Montreal. If you guys ever go to a casino, I think it's the last bridge, or not the one that's got the stay cable, but the one that has like just a box girder. If you stop and go underneath the bridge, if I'm not mistaken, that's where you'll see the steel. It looks like it was painted brown. Well, it's not painted brown. It's actually corrosion that is actually forming on the surface to protect the steel from further corroding, okay? And of course, again, like for temperature effects, you're going to use the top-notch steel. Now this here, okay, quench steel, okay, is very, very strong, okay? In other words, you're looking at about 700 MPa, okay, as opposed to here 350 MPa. But the problem with this one is that it's not very ductile. So when ductility is not an issue in your design, in other words, you don't want it to deform and so on, and you want to have to use some very high strength steel for a very specific application, then you'll use quench steel. But the thing is that, like I said, this here is it loses the benefit of being ductile. And do you understand what I mean by ductility? Who doesn't understand the word ductility? Does everybody know what ductility means?
I mean, if you could explain it.
Pardon?
If you could explain it, that'd be great.
Okay, ductility means the material has the capacity to stretch before it fails. Okay, so in other words, if I have a steel beam here, okay, if I have a steel beam here, like this, okay, and if I use W steel for this beam, okay, when I apply a load here, okay, this material is going to start deflecting, okay, and as it approaches its yield strength of 350 MPa, okay, it's still going to stay elastic, but then when it exceeds 350 MPa, this thing's going to start deforming very much. So people that are standing on this floor made with this beam and they start seeing an excessive deflection, they say, oh my God, something's wrong here. This thing's not, and they have a chance to get out. So by having this beam being able to deform without collapsing, then you know that you got this additional safety measure built into your design that can warn people that something's wrong with the structure. And that's what ductility does. It allows the material to deform a lot before it actually fails. Whereas a brittle material like concrete, okay, it does not deform very much. And then once it's reached its breaking point, it breaks suddenly. And that's what concrete does. And this quench steel, unfortunately, does lose some of that characteristic of being able to deform excessively. And therefore, I wouldn't recommend you using it unless ductility is not an important factor in your design, okay? So that's what ductility is. Okay, so these, like I said, this is the one we're gonna always be using, the W, okay? But just to keep in mind, there are 6 other types of steel that are available for structures. And of course, these ones here are mostly for bridges, okay? Cold temperature. And like I said, very few times, I've never used Q myself, but I know that it is available and it's very, very strong. Okay, so that's the steel that we have. And like I said, we're just gonna worry about that one. And now, one last thing I wanna talk about. First of all, how are we doing in time? Oh, we're doing great, lots of time, okay. Now, I like, this is also, I copied this right out of my steel handbook, okay. This is something that you guys should get familiar with, okay? And this is a good glossary of the different names of the members that you find in a steel structure, okay? Now, for example, unfortunately, the only thing I don't like about this diagram, instead of, for example, starting with number 1 here and then systematically going, sequential, like you got to jump all over the place to try to find it. But just so that you guys can get an idea of the glossary of a steel building, okay? I mean, here, you look at anchors, okay? So for example, let me just, okay. Anchors for beams and open web steel joists. So this is what they're talking about. If you're going to have a steel beam here, okay, and it's going to get encased into your masonry wall, well, these are the anchors that you would place so that when you put your masonry here or your bond beam, this all becomes encased and it helps to anchor the beam to the wall. Okay, so these are the anchors. Now, anchor rods, of course, these are the anchor rods that you would be placing, you know, into your foundation, so that when you come and place your column, the column is going to be able to, you know, be held in place by your anchor rods. So those are your anchor rods. Clear all drawing, and then of course you have, we are going to actually be designing these things. These are base plates. In other words, the column comes down, and in order to help distribute the load that the column has onto your concrete pier or foundation, whatever it is, you can have a base plate to help distribute. So we are actually going to be designing these in this course, the base plates. And of course, now you have number 4. Now, when you have a single member like this, they call it a beam. This is called a beam. And then when you have a series of beams being supported by another beam, well, then they call this a girder. Okay, so people say, what's the difference between a girder and a beam? A girder is a one that supports a number of beams. So number 16 are your girders. Okay, so this is a girder and this is a beam. So if you know that there's one or more beams being supported by another beam, that you'll refer to that as a girder. And if it's just one member, you can refer to it as a beam. Okay, so those are girders, and clear the drawing. So, now, bolts, bracing. I just want to okay, so this is something we'll talk about in the lab. These are called open web steel joists. Okay, this is open web steel joists. That's how it's abbreviated. As a matter of fact, we'll talk about this for our project, the open web steel joists. And of course, here, what I want to show you is that you have, for example, number 17, okay? These we're going to have in our project. These things are called girts, okay? And then when you have a series of, you can have exactly the same shape or the same profile, and if you put them, these members on a roof, these become purlins. So like when you have members on a roof that are closely spaced together, what I mean by closely spaced together, by about a meter and a half, and they're made, you will refer to those things as purlins, and therefore people right away will know that you're going up on the roof, okay? So these are purlins, these are girts, and so on. Now, if ever, for example, if ever you see this is very, very common, you know, you see a reinforced concrete structure go up, okay, on the different floors, and then all of a sudden you look outside and they have these angles, okay, that are attached to the concrete structure, and that's where your masonry is going to be sitting down. Well, those are referred to as shelf angles. Okay, so when somebody says something's wrong with the shelf angle, right away in the back of your mind, oh, it's that thing that supports the masonry, okay, on the building. That's called a shelf angle. As a matter of fact, number 30, where's number 30? A shelf angle attachment to, well, this is to a steel frame, but where very, very common to attach in concrete high rises at every floor. After you get past the 3rd floor, you start seeing these shelf angles. This is something else we'll talk about in our project. These are called sag rods, and I'll tell you what those are used for when we talk about our project, okay? These are stiffeners. We will actually be designing to see if we need these things. These are stiffeners, web stiffeners. And oh yeah, and of course, see, this is like this is probably an I section, because you see like there's like a bit of a crane or a hoist that's being, you know, so this is probably an I section. And you know, if ever you're stuck and you can't find concrete to do your foundations, remember you can do a grillage like this, and you can make a foundation out of steel if you need to. You know, as long as you help distribute the load, it works. And what else can I talk about this here? Does anybody have any questions? Oh, here. As soon as you have a member that goes over an opening, what do you refer those to? Well, that's a lintel, okay? So in other words, lintel are all supporting elements that are going to be help to, you know, bridge across an opening, whether it's a door or a window. Those are lintels, number 22. Yeah, lintels. And of course, this here is, we'll talk about this in the lab. This is steel decks. And you'll notice that okay, they don't show it here, but you notice that when you have columns, okay, of course, the most obvious one, I should have referred to this as a column. Okay, this is a column. And if you notice that when the column, they don't show it here, but you'll see it here. When the column goes for a number of stories, right? Look how they're connected. Okay, so the columns are not connected right at the floor level. They're connected slightly above the floor, and then they're kind of spliced together with this type of connections. Okay, so when the columns are continuous, they'll go right through the floor, and then they'll be connecting with these plates here, and then the other column is going to get attached to it, and it goes up. So this is very typical for 5, 6, 7-story buildings, and especially like in New York City. All the high-rise in New York City are made with structural steel versus Chicago. All the high-rise are made out of concrete. Just to give you an idea, the difference between the two cities. And of course, these are braces. Okay, so this gives a lot of stability to your structure. We're going to be designing braces for our project. And is there anything else here that you guys might be interested in knowing about? So this is a nice little, diagram that helps you, relate to the glossary of structural steel. So like, in other words, this is number 12. Okay, this is the stopper for the overhead crane, number 12. Crane girders, rails, and stoppers. So this would be a rail for, okay. And then, for example, these are brackets. Sometimes the bracket would be right underneath here to support the railing. Okay, so these are brackets. And anything else that I can talk about? Number 13, what's number 13? Door frames. Yeah, we'll be putting some door frames in our project. Is there anything else? Oh yeah, here. These are shear connectors. You see these things? These are shear connectors. In other words, what they do, these especially these ones, these have a very specific name. Those are called Nelson studs. Okay, and in the lab, I'm going to show you some of these things. Okay, Nelson studs, and what they do is that they are welded to the top flange of your beam or whatever. Okay, or your girder, and then when they pour the concrete. When they pour the concrete and the concrete acts compositely with your beam because it's a composite section, well, shear connectors, what it does is that it guarantees that the concrete will not slip over the beam and they'll work together. That's what the shear connectors do, okay? So these are shear connectors. And what's number 20? Oh, this is your HSS for the interior columns, you understand? So, 9 times out of 10, if not 99 times out of 100, interior columns are always designed with HSSs, square HSSs as opposed to Y flange, and exterior columns are always designed with Y flange or rectangular HSSs and never square. Oh, and then of course here, okay, so these are trusses, okay, so top chord, bottom chord, web members. And this, of course, is your number 22 is your steel deck, and we'll talk about that in the lab, the steel deck and so on. So this gives you a good overview, okay, of the, like I said, of the glossary that we tend to use in structural steel. And I don't know what else, what's number 14? Oh, floors, okay, floors and plates. Does anybody have any questions that they might be curious about?
All clear.
All clear. Yeah. Well, see, Omar, was that you?
Yes.
Okay. Well, Omar, like those nights where you're tossing and turning and you can't fall asleep, right? Well, you make a copy of this, you put it in front of your face, and I can guarantee in 3 minutes you'll be asleep. How's that? Sounds good. So like I said, this is a nice little thing, and see separate diagram for other suppliers. Okay. Last viewed. Okay, and I think that's it, guys, for today. And is everybody okay? Let me just stop sharing here because it's done. I want the video to be stop sharing. I'm going to put this on.